Thank you, Anna. It's a real pleasure to be here. I'm also affiliated with CSE, actually. With ECE, I'm sorry, Electrical and Computer Engineering Department here. And it's always a pleasure to cross the river to come here. As Anna remarked, the machine learning and AI is having an increasing effect on society, and a very interesting development over the last few years is that NYU as a whole has taken a big role in that revolution and has become kind of a focal point of a lot of interesting things happening in that area, partly because of the Center for Data Science, to which many members of Tandon are affiliated, and also because there's a lot of people working on deep learning and sort of the new AI, including here at Tandon, Anna being one example. I think there is a huge amount of opportunities, particularly in the engineering. So my background is actually electrical engineering. I studied electrical engineering as an undergrad. My specialty was actually chip design. It's very odd, but that's what I studied at school. And only later kind of shifted towards things like optimal control, and then kind of led me to neural nets and AI. So I view myself as an engineer as well as a scientist, and always like to build things, which is really the purpose of engineering, inventing new techniques and building things. Okay, so let me start by kind of a sobering comment that I heard from Josh Tenenbaum, who is a cognitive neuroscientist or cognitive scientist at MIT. He was at a conference I was at also a few months ago, and he said, all those AI systems you see nowadays, none of them is real AI. And what he means by this is that none of the AI systems that we have today can match the ability of biological systems, animals and humans, to learn how to survive, deal with variability of data in the world. So we can do a lot with current techniques, but we're very far from really sort of reaching the goal of making machines really intelligent. And so the first part of my talk is going to be a bit of a state of the art and a little bit of history as well. And the second part is going to be about the challenges of the future. And I think areas like robotics have a big, important role to play there, because that's where the important problems pop up. I'll come to this in a minute. Okay, so AI today really is supervised learning. What supervised learning means is that you have this is engineering school, so I use an analog synthesizer as a model for a learning machine. It's a learning machine really is a parameterized function. You show it an image, and you run the calculation through it, and it produces an output. If the output is what you want, you don't do anything. If the output is not what you want, you tell the machine, here is what the correct output is. And what it does is it figures out how to adjust its parameters so that next time around it sees the same input, the output gets closer to what you want. Okay, so let's say you want to classify images of cars from images of airplanes. Show an image of a car, and the machine doesn't say car, just adjust all the knobs, of which there could be millions, so that the output gets closer to what you want. And the interesting thing about this is that if you build a machine in such a way that it has enough power, if you want, the machine will eventually figure out what the concept behind a car and an airplane is, and kind of will be able to classify any car and any airplane, including if there is a lot of variability. The example of chairs here, where there's a huge amount of variability between the appearance of chairs. And the reason why that is because of essentially the appearance of deep learning over the last, or the popularization of deep learning over the last 10 years or so, even though work on this started about 30 years ago, and restarted more recently about 15 years ago. The world kind of started learning about this, about 7 years ago or so, not even that. So classically, when you wanted to do pattern recognition, you would feed the image to a feature extractor that would generally be built by hand, and then you would plug a trainable classifier on top of it. So those kind of pink painted boxes are supposed to mean that they are adaptable, that it can be trained. Right, so at the top is kind of the classical model of pattern recognition, and it's used still very, very much in a lot of practical applications. of machine learning today. At the bottom is kind of the deep learning model, and the idea of deep learning is that you build your model as kind of a stack of adaptable, trainable, parameterized modules, and you train the entire system end to end, so as to minimize some objective function that measures the discrepancy between what you want and what you get. But the point is, the entire system is trainable, and that allows it to kind of process the data in sort of a hierarchical way, and I'll come to why that's a good idea. So the next question you have to ask is, what do you put in those boxes? And it's deceptively simple. Essentially, a simple neural net is a succession of such boxes, and there are really two types. One type is just a linear operation, right? So imagine a text, an image, or an audio signal is coded into a vector. You take this vector, multiply it by a matrix, you get another vector, possibly of a different size. Okay, that's a linear operator. And the coefficients in this linear operator are going to be the knobs that we're going to adjust by learning. So that produces another vector. You could think of each component of this vector as being a weighted sum of the component of the input vector, weighted by the corresponding row in the matrix by which you multiply this vector. Then the second operation is a pointwise nonlinearity. And in recent incarnations of neural nets, very often this pointwise nonlinearity is the one shown on the top right. It's called a ReLU. It's really half-wave rectification. The nice thing about talking to engineers is that I don't have to explain what half-wave rectification is. Not so for computer scientists. So you have linear operation, pointwise nonlinearities, which are very simple, and then you stack multiple stages of these pairs of operations, linear, nonlinear, linear, nonlinear. You can show that with only two layers of these, so linear, nonlinear, linear, you can approximate any function you want as close as you want, as long as the middle layer is large enough, okay? And that's something that people have relied on for many years, arguing for the fact that you never need more than two layers because you can approximate any function you want with two layers. That actually is not entirely true, because for most functions you want to compute, the middle layer might need to be extremely large. And so classical models like, or what have become classical models like, say, kernel machines, support vector machines, things like this, are limited to two layers. In fact, only the second layer is really adaptive. And that's what limits their power, is the fact that they can only do basically two steps of computation and one nonlinear step of computation. So it turns out there's a lot of interesting functions that require multiple nonlinear steps of computation, and that's why deep learning is really interesting. And it's very difficult to kind of turn this into a theorem and sort of have some theory about why you need multiple layers, but intuitively it makes complete sense. Most functions require multiple steps. Computer scientists know this, right? It's very rare that you can write a program to compute a function that will only require two instructions, right? Generally, you have loops, you have things like that, right? Okay, so training, supervised learning really comes down to minimizing an objective function. You show an example to the system, compute the output, compare with the output you want. That gives you a value for the cost function, the objective you want to minimize, the error between what you want and what you get. Adjust the parameters a little bit, then show another sample, adjust the parameters a little bit, then show another sample, etc., etc. And if you do this, what you're doing in effect is what's called a stochastic gradient optimization algorithm, shown at the bottom, where you basically replace each parameter by its own value minus the partial derivative of the loss function you want to minimize with respect to this particular parameter multiplied by some constant, a step size. And because you do it on the basis of a single sample, that's called stochastic gradient, because you get an estimate of the gradient of the objective. Really, the objective you want to minimize is the average of all the samples, but because you do it one sample at a time, you get a noisy estimate every time. Or you do it with a small batch of samples at a time, you get a noisy estimate, so it's called stochastic gradient for that reason. And so pictorially, you can think of the cost function as being, some sort of landscape in a high-dimensional space. And what this algorithm does is kind of find the minimum of that, the valley, the bottom of the valley in that landscape, but kind of stochastically every time being given kind of a noisy estimate of the direction of steepest descent. So next question you might ask is, how do you compute this gradient? And there's the so-called backpropagation algorithm, which I'm not going to go through because it would take too long, and many of you, I'm sure, know about it. It's basically based on chain rules. So it says if you know, your network is basically a graph of computational nodes, and you know how to compute the output of each node, of computational blocks here in this case. You know how to compute the output of each block as a function of its inputs and its internal parameters. And it turns out if you know the gradient of the loss function with respect to the output of that module, you only need to multiply by the Jacobian matrix of that module with respect to its input or with respect to its parameters to get the gradient with respect to the input and with respect to the parameters. So that gives you a suggestion that you can have some sort of recursive algorithm that goes backwards, through the graph and kind of propagates gradients this way. And it's called the backpropagation algorithm. It's basically just chain rule. But it turns out, if you express it graphically, you express your system as a graph of networks. You don't have to figure out how to compute the gradient. As long as your system knows how to compute the gradient for each module, you can assemble very complex networks and not worry about how to compute the gradient. That will be done automatically by the software you use. So all the deep learning framework, basically what they do for you is they allow you to build a graph of those networks, and then they automatically compute the gradient for you. Okay, so linear operators are good, but if you have an image might have, 1 million pixels, if you multiply an image of 1 million pixels by a matrix, and the output is also 1 million variables, let's say, that's a big matrix, right? 10 to the 12 terms. So what we need to do is essentially reduce, put some constraints on this matrix so that it becomes manageable. And convolutional nets, which are used somewhat universally now for image recognition, as well as for all kinds of other applications like speech and even text, translation, things like this, the main idea behind that is to basically constrain the matrices so that they're basically tuplis matrices, and that they can have fewer parameters and reduce the amount of computation. So again, the nice thing about talking to electrical engineers is that I don't have to explain what convolution is, but the basic idea of a convolutional net is you take an image and you take a neighborhood of pixels, and you have a set of coefficients that you multiply this little patch of pixels by, and that gives you a weighted sum. Okay, that's one term in the output. So that gives you one output value, and then you swipe that little window of pixels over the entire image, and every time you compute the dot product with the coefficients and record the results. So that's a discrete 2D convolution, and you get if the input is here at the bottom right, you see the little convolution kernels, the set of coefficients, and you see the result here. That's called a feature map. Then you pass the result to a nonlinearity, say a ReLU or sigmoid or something like that. So at the bottom here on the top left, you see the image. Then you see the 4 feature maps that are the result of convolving the image with 4 different kernels. And the coefficients of those kernels are the result of learning, right? They're learned with backpropagation all the way through. And then there's a second operation called pooling, which consists in sort of aggregating the response of the filter over a small area by a max or an average or a L2 norm or something like this, and then reducing the resolution. And the reason for this is to impose a little bit of shift and distortion invariance in the system. And this is very much inspired by biology. We talk about convolutions and invariance and blah, 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 but in fact, the architecture of this is completely suggested by the architecture of the visual cortex, this classic work in the 60s, in fact, Nobel Prize-winning work by Hubbell and Wiesel about the architecture of visual cortex, where they showed that neurons in the visual cortex of cats look at local areas in the visual field and are basically repeated all over the visual field. So that's where the idea comes from, and there were models that tried to emulate this, back in the 80s, Fukushima's neocognitron, for example. Neuroscientists call these simple cells and complex cells, the sort of convolution-like operation and the pooling. So here is a convolutional net in action. Each vertical column is a different layer. You see the input on the left, and if the input shifts by 4 pixels, then the third layer after pooling shifts by 2 pixels because it's subsampled by a factor of 2. And then 2 layers up, it's shifted by 1 pixel, and then a couple layers up by maybe 1/2 pixel or something like that. So as you go up the layers, the amount of distortions caused by a shift in the image or distortion in the image is reduced and is easier to model, which is why those systems kind of are more amenable to doing image recognition or kind of somewhat invariant recognition. So that seems like an obvious concept, but back in the 90s, very few people were convinced this was a good idea. So for example, this is a picture taken in 2005, which was the dinner resulting from a bet between Larry Jekyll, sitting on the right, and Vladimir Vapnik, who is in the back here, whom I think you'll hear talk at this seminar in a few weeks. So he's a former colleague of mine at Bell Labs. And the bet, Larry Jekyll was the head of the department at the time, and Jekyll bet one fancy dinner that by March 14, 2000, this was in 1995, people will understand quantitatively why big neural networks working on large data sets are not so bad. Understanding means that there will be clear conditions and bounds and things like this, the kind of theoretical arguments that Vapnik likes. Vapnik bets one fancy dinner that Jekyll is wrong. But if Vapnik figures out the bound and conditions, Vapnik still wins the bet. So this was a thinly veiled attempt by Jekyll to convince Vapnik that he should do the theory for neural nets. He completely failed. And he also lost the bet, because we still don't quite understand really kind of the generalization properties of neural nets. I mean, we understand they work, there's no problem with this, but not to the same extent as simpler models, just because, they're much more complicated. And so we don't have simple theory for it. We have theories, but they're not that useful. There's a second bet. Vapnik bets one fancy dinner that by March 14, 2005, no one in his right mind will use neural nets that are essentially like those used in 1995. Jekyll bets one fancy dinner that Vapnik is wrong. So Jekyll lost the first one, Vapnik lost the second one. And so in 2005, there was a dinner, and they shared the bill. And Léon Boutou and I, Léon Boutou is the man on the left here, Léon Boutou and I just enjoyed the dinner. Okay, so, since there's quite a few people here, I see fortunately here the first row working on robotics here, I thought I'd talk a little bit about some robotics project that we did. And this is a little historical, going back about 10 years, even more. The end of the project was about 10 years ago. This was a project called Lager, Learning Applied to Ground Robots, sponsored by DARPA. And the idea was to use machine learning to drive robots of the type you see on the top left off-road. So the system should be able to, through vision, kind of figure out what's an obstacle and what's not. And you can do this with stereo vision for short range, but it doesn't really work with long range, because with stereo vision, you can only, depending on the baseline of the two cameras, you can only figure out if something sticks out of the ground about 10 meters out, but not much more than that. So what you see here in the middle column are the result of applying stereo vision to this. And it stops after 10, 15 meters, whereas if you apply the neural net, it's monocular, so it works all the way. And the cool thing about this is that you can train the neural net with the data produced by the stereo vision system. So you don't have to explicitly supervise it. You basically let the robot run, collect data from stereo vision, and then use that to train a monocular system to tell you whether something is an obstacle or not. And so it was a convolutional net, which, the idea of this was that you would apply the convolutional net basically on small patches over the entire image, and it would classify every pixel if you want. So it's a task in computer vision that we call semantic segmentation, which consists in categorizing every pixel in the image by the category of the object it belongs to. So this was running on, this was a robot built by NREC at CMU around 2005, and so the processors were not what they are now, no GPU or anything. So we could run the neural net at about 1 frame per second. So we had a short-range stereo vision system for kind of avoiding unexpected obstacles, and then the long-range vision system would run at about 1 hertz. And so this is the robot. This video is accelerated twice, and these are annoying PhD students making the life of this poor robot impossible. But they're allowed to do that because they actually wrote the code. And this is Pierre Samanet, who is now working on robotics at Google Brain in California, and Raya Hetzel, who leads the robotics research group at DeepMind in London. So after this, we decided that we could do semantic segmentation for real. So instead of, whoops, I'm not sure why my slides are shifting without me telling it, but anyway. So we decided that we would work on semantic segmentation for real and essentially have a system that labels every pixel in an image, not as to whether it's traversable or not, but with the category of the object it belongs to. So you have an image like this, and you'd like to be able to tell whether it's the road or a car or a building or the sky or trees or whatever, or pedestrians. That's kind of important. And so eventually we built such a system. It's, again, a convolutional net kind of swiped over the entire image. You can run this very efficiently. With Clément Farabet, who is now the VP of Machine Learning Services at NVIDIA, he implemented an FPGA board that ran this system at about 20 frames per second. And this is kind of a demo of this. This is state-of-the-art at the time, down Washington Square Park. Some of you might recognize. This is Washington Square Park. So it's making stupid mistakes, like it's classifying, some areas of Washington Square Park as desert or beach. There is no beach I'm aware of there, but it would certainly make the campus more attractive. So, it's not perfect, and since then, those technologies based also on convolutional nets have made a huge amount of progress, but, this was 2010, roughly, and we could run this at 20 frames per second. So I gave various talks about this around that time, and it gave some ideas to people working on self-driving cars. They realized perhaps they could use this for self-driving cars. So in particular, there's a company called Mobileye in Israel that was working on vision systems for cars, created by Anon Shashua, who was a professor in computer vision at Hebrew University. And they started playing with convolutional nets, and were getting much better results than with whatever technique they were using before. And they had a problem because the chip they had designed wasn't really designed to run convolutional nets. So they kind of had to shoehorn convolutional nets onto their current chip. Now they have new chips that do differently. But it worked well enough that the Tesla cars that appeared in 2014, 15, actually used their chip for autonomous driving. After that, they divorced for various reasons. That also prompted NVIDIA, who builds the GPU cards, to get into the business of self-driving cars, because they realized, they could, build the hardware for this. And they also realized that they couldn't just sell the hardware, they had to build software on top of it. In fact, one team that does research on self-driving cars at NVIDIA is, because, former colleagues of mine from Bell Labs and works in Holbert, New Jersey, the same building where I used to work at Bell Labs. And they're doing pretty amazing stuff there. And his husband actually works there too. Okay, so what happened in 2012-13 is that people figured out, first of all, there was much bigger data sets that became available, like ImageNet for image recognition. So ImageNet is a data set with 1.3 million training samples. It's got 1,000 categories of objects, that are sort of a dominant object in the picture. And this is the kind of data where convolutional nets really shine. Before that, the data sets were so small that, techniques that built more things by hand were actually more successful than convolutional nets. We couldn't really get kind of, record-beating performance with convolutional nets before that. But with large data sets, that really kind of blew everything out of the water. And the second reason was the efficient implementations of convolutional nets on GPUs, which allowed us to build much, much bigger convolutional nets. So the work by our friends at University of Toronto, Alex Krzyzewski, Ilya Sutskever, and Jeff Hinton, really kind of opened the eyes of the computer vision community on this and sort of created a kind of a revolution, which is funny because in 2011, we submitted a paper on this semantic segmentation to CVPR, and it was rejected, mostly because people had no idea what a convolutional net was, the reviewers, and they didn't believe that technology that they'd never heard of could work so well. 3 years later, maybe 3-4 years later, 2015, 14, you cannot get a paper accepted at CVPR unless you use convolutional nets. So, it's been a big revolution. Now, what's happened over the last few years is that so many people got interested in this that they all came up with really cool ideas, new architectural ideas on how you kind of assemble those functional blocks into in various ways. And the latest architectures of convolutional nets for image recognition have something like 50 layers or 100 layers. They use this idea called ResNet, originally proposed by Kaming He from Microsoft Research Asia. He now works at Facebook in California. And it kind of this evolution has led to incredible improvements in recognition rates. So on ImageNet, for example, before convolutional nets, the best error rates were around 25, 26%. This is, you count an error when the correct category is not in the top 5 among the 1,000. Then 1 year later, the Krzyzewski paper brought this down to about 15. 1 year later, it was around 10. 1 year later, it was around 5. Now it's below 3. And that's superhuman. So if you ask people to categorize those images, they'll make just about as many mistakes. And most of those are on images that are ambiguous in the first place. You don't know what the relevant object is. So one question we might ask is, why is it that makes convolutional nets and those hierarchical multilayer structures actually good? And in my opinion, it's probably because they reflect the compositionality of the real world. So the real world, particularly the perceptual world, is compositional in the sense that an object is formed of parts, and parts are formed of motifs, and motifs are formed of collection of edges. And so if you have at the low level a sort of oriented edge detector, which is what those convolutional nets end up learning and what your brain is doing, and what every, actually, even handcrafted computer vision system will do, then you can detect combinations of those edges to detect, common shapes like corners, circles, grating, things like this. And then those assemble to form parts of objects. So you detect combinations of those. And that's kind of what this architecture of convolutional net reflects, with a pooling operation that allows the position of those little features to kind of vary a little bit. And so you get this sort of elastic perception. And so it sounds like a conspiracy that the world is so designed that it's easily understandable by architectures that happen to fit in our brain case, which led Stu Geeman, who's a applied mathematician at Brown, to say the world is compositional or there is a God. This is kind of a play on something that Albert Einstein said, that he said that the most incomprehensible about the world is that it's comprehensible. The world could be completely random and there was no way we could make any sense out of it. And so it seems like a conspiracy that there is some understanding we can have of it. Okay, so moving on to slightly more recent work. This is a little bit of a snapshot of the state of the art of what people can do in computer vision. And this is some work done at Facebook AI Research in California, in Menlo Park, a technique called masked RCNN. And this is, again, sort of a semantic segmentation system, but it doesn't just label each pixel with a category. It labels it with the instance of the object. And it gives you a mask for the object. So I'm not going to go into the details of this architecture, but it's conceptually quite simple. You can do things like this. So it will, again, it's kind of a sliding window convolutional net. It looks at multiple scales, and it kind of focuses on different areas. And the output is not just a category for the pixel in question. It's also a mask of the object that it believes it's looking at, okay, for every location. So you put this together, and you get, a mask for every object in the picture. The baseball bat, the dog at the bottom, the people, etc. They are individual people. The wine glasses, the wine bottle, the computers in the back, the table. You can count the sheets, etc. I mean, it works amazingly well. And this is, in my opinion, really one of the most kind of impressive progress of the last few years in computer vision, showing what people can do with this. We can track key points on bodies and sort of reconstruct the pose. So this is the latest result. This code is open source, by the way. So if you go to this URL, you can just download the code, play with it. You can train it to your own purpose. It's all C++. It's pretty cool. You can apply convolutional nets to 3D data. This is some pictures from also a semantic segmentation competition, actually, run by Stanford, I believe, where a team from Facebook in Paris actually won that competition using 3D convolutional nets. And the problem with 3D is that when you have an occupancy map or a point cloud of 3D points from LiDAR, for example, or a depth sensor, most of the voxels are empty. And so if you run a convolutional net on the entire volume, you kind of waste your time just multiplying zeros with, with other numbers. So they figured out a way to kind of just follow the areas where there is voxels that are non-empty, and thereby kind of increasing the efficiency, and they got really good results with that. In fact, they won the competition. Just to show that convolutional nets can be used for something else than pixels, one of the systems that Facebook uses for translating languages from one language to another is actually a convolutional net. It's a gated convolutional net, so it's a little more complicated than traditional convolutional nets. The architecture is shown on the right. I'm not going to go through it, but it basically takes every word as a vector, essentially, and it learns the mapping from words to vector as well. And then that goes to a convolutional net, and then this convolutional net has some gating mechanism that can sort of regurgitate words in a different language in the right order. So if you translate, English to German, you remember to put the verb at the end and stuff like that. So it's interesting that something that was designed for perception and vision can actually be used for producing sequences and that are not pixels. But text has a common property with images, which is that there's kind of local correlations, right? The one word can follow another, and there's some correlation between neighboring words, but faraway words are less correlated. So it's kind of like pixels in images. Now, a lot of things that we do at Facebook, and I wear two hats. I have one foot at NYU, one foot at Facebook, or I should say 1.5 foot at Facebook and 1.5 foot at NYU. Is that all the research we do is open. We publish everything, and we distribute a lot of code in open source. So the one that's probably the most useful at the moment is PyTorch, which is a framework for deep learning. It is very flexible. And it would be nice if my laptop didn't die. Okay. Apologies. All right. Okay. Now, deep learning is this idea of assembling modules in kind of a fixed graph. But really, what people are moving to is something some of us would call differentiable programming. And the idea there is that you don't want this graph of operators to be fixed. You want it to be defined by program. And you might want it to be dependent upon the input you're looking at. So for every new input you're seeing, the architecture of the graph will change. And so what is it called differentiable programming? It's because basically you write a program that computes the output, and this program calls functions that could be the equivalent of those modules, functional modules I told you about. And there is, in the background, something that figures out how to basically backpropagate gradients through your program. So that whatever program you write, or I should say subgradient for the mathematicians in the room, because a lot of those functions are not entirely differentiable. So let's call it subgradient and be done with that. But the idea that the program is data dependent and builds the graph dynamically, and you can still propagate gradient through it. So let's call this differentiable programming. You could think of this as a slight generalization of deep learning, the same way probabilistic programming is a generalization of probabilistic graphical models, for example. And people are interested in this, particularly in the context of natural language processing or reasoning, because we think that's kind of required for certain types of reasoning. So an example of this is neural nets that are augmented by modules that basically act as a scratchpad memory, like a RAM, if you want. And so that's a kind of a concept that popped up a few years ago with the memory network idea by Jason Weston, who is at Facebook. Stack augmented RNNs by Julien Nikolov, also at Facebook. Neural Turing machines and differentiable neural computers by Graves et al. From DeepMind. Those ideas kind of popped up more or less all at the same time, within days of each other on arXiv, which is funny. The basic idea is that you have a recurrent neural net, so a neural net that can feed its output back to its input if you want, so it can have some dynamics. And it's accessing a memory on the side. So a memory is just a different type of set of modules that behave in a particular way. And this, again, several architectures, which I'm not going to go into the details of, but just talk about this idea of differentiable memory. So think of a circuit of a RAM chip, okay? A RAM chip has an address decoder, which basically compares the input address with all 2 to the n possible bit configurations and activates one line in the chip memory. And then what you read out is the weighted sum of all the memories, except all the weights are 0, except for the one whose row is addressed. So the differentiable memory used in those memory networks is exactly the same idea. The input is a vector. You compute the dot product of this vector with a bunch of key vectors, which are that's like the address decoder. So the dot product gives you, how well the input vector matches each of those keys. You get a bunch of numbers correspond to the dot products. You run that through a softmax, which turns this into a bunch of numbers between 0 and 1 that sum to 1. It's kind of like a Gibbs distribution. The formula is on the left. And then you use those coefficients to, in a weighted sum of values, which themselves are vectors produced by the memory. So what you get is a weighted sum of the values in the memory weighted by those coefficients, resulting from the dot product of the input address with each of the keys. So it's kind of a soft associative memory if you want. And the cool thing is that you can propagate gradient through that. You can learn the keys, you can learn the values, etc. So you can build neural nets. So this is kind of a recurrent neural net unfolded in time, which accesses this memory 3 times in this case, if you look at the right part of the picture here. So you get, for example, you want to build a system to answer questions. You put a question at the input, which is really encoded as a vector. And then the system sort of computes an address, accesses the memory to see if the answer is there, then gets the answer, runs the recurrent net once or twice, then accesses the memory again, runs the recurrent net, access once or twice, etc. And that would allow the system to basically access the memory multiple times if it needs to connect multiple facts to answer a particular question. So my colleagues at Facebook came up with this thing called the Baby task. It's kind of hard to read, but in the middle at the top, there is a little story. Sam walks into the kitchen. Sam picks up an apple. Sam walks into the bedroom. Sam drops the apple. Where is the apple? And the answer is in the bedroom. So you have to kind of track, what goes on, etc. You have to make simple inference. Brian is a lion. Julius is a lion. Julius is white. Bernard is green. What color is Brian? If you assume all lions are white, Brian is white. So they came up with 20 different types of questions of this type that people might want to answer, and or want machines to answer. Training a memory network to answer those questions, they can basically solve 19 of the 20 types. There's another type of network called entity network that can solve all 20 that we came up with more recently, but which I'm not going to go into. It's very similar. It's also kind of a memory augmented neural net. So that's really nice because that's the idea of kind of marrying reasoning with learning. And reasoning is something traditional AI was very strong at. So traditional AI, expert systems, rule-based systems, this is basically completely concentrated on the whole idea of doing reasoning properly. But then there's the problem of knowledge acquisition. How do you feed the machine with enough knowledge to reason properly? And that was always the main problem, the main issue with expert systems. It's how much effort it takes to actually reduce everything to rules, etc. So what you'd like is machines to be able to reason, but at the same time learn how to do that and learn facts. Here's another example, also done at Facebook in Menlo Park by Justin Johnson, who was at the time an intern, and a whole bunch of characters from Facebook. And here the problem is to answer questions like, the picture at the bottom here, is there a matte cube that has the same size as the red metal object? So to be able to answer questions like this, you're going to have to count the number of objects of a particular type, detect them first, etc. So they came up with this architecture, and people since then have come up with even better ways of doing this, but the idea is a little similar. So imagine you have a question that the system needs to answer, something like, are there more cubes than yellow things? So you take the image, you run a convolutional net on it, which we're going to train through this whole system. Then what you'd like is a little block, one of those green blocks here, that filters colors, another one that filters by shape, and detects cubes. The first one filters the yellow objects. Then there is a block that counts those objects. Then there's a block that compares those two numbers, and you get the answer to your question. The problem is, it's one of those examples where this graph of operators needs to be dynamic. It needs to be determined by the data. And so what they have here on the left is the question goes into a recurrent neural net that then spits out a specification for a graph, essentially. It's a kind of a tree type, it's sort of a graph-like syntax that specifies a graph. And it's kind of hard to backpropagate to this operation. More recent work on this by others, by Aaron Corville at University of Montreal, for example, have done this in a fully differentiable way. So here there is a bit of hocus pocus you have to do to train this system end-to-end. But the wonderful thing is that the only way you have to train the system is you give it a question, you give it an image, you give it the answer, and it basically figures out how to kind of organize all this. It needs a little bit of prompting at the beginning to tell it what the graph looks like for a few examples. But it's able to generalize pretty well. So that's one of those kind of really eye-opening examples where you can have essentially a neural net producing another neural net dynamically and then have this neural net solve a particular problem. And it seems like, it sounds intuitive that we might have something like this in our head, right? We face a new situation, we kind of configure our reasoning engine to kind of figure out, analyze the current situation. Let me skip ahead a little bit. When I'm skipping ahead, I have to apologize to Anna because it's work that she and I did together a few years ago. But I want to get to obstacles to AI. So, as I said before, animals and humans learn much more efficiently than all the machines that we have. And one may wonder what kind of learning algorithm does the brain use, or what kind of principle, what kind of paradigm. It may not be just a question of algorithm. And one thing that humans and animals seem to have is some sort of common sense ability, right? The fact that we kind of know how the world works, and so we can fill in the blanks for a lot of things. We don't have to be told everything. Right now, most of you are seeing my left profile, but you can figure out what my right profile looks like because you know that faces are mostly symmetric. You have a blind spot in your visual field where your optical nerve punches through your retina, and you're not even conscious of it because your brain kind of fills it up. We have a very good ability to predict the future and predict the consequences of our actions. That's what allows us to plan ahead. In fact, you could say because of this that the essence of intelligence is really the ability to predict. It's the ability to build models of the world, right, by learning, by observation, by interaction. So perhaps what we need our machines to do is this kind of predictive learning. It's a little, the phrase here does not exactly reflect what it means. Perhaps a better name would be imputative learning, but that sounds a little pedantic. So it's basically the idea that the system should learn to predict every variable it doesn't currently observe from all the variables that it currently observes. So predict the future from the present and the past. Predict all the things you can't directly observe right now, but you might observe by moving your head. So right now, some objects are, the front of the stage is hidden behind the lectern, but I can move and figure out what it looks like. So I can sort of, train my brain to predict what it looks like and see what it is. My brain certainly can predict what the view is gonna look like if I shift my head 20 centimeters to the right. And in the process of learning how to do this, we probably developed the notion of depth, right? So depth can be learned naturally by predicting how the world changes when you move your head. Or if you look at the world with two eyes or so. But even if you had one eye, it would still work. And so, we learn this as babies, right? We look at the world, we can hardly act on the world when we're babies. But we learn a huge amount of stuff about the world just by observation. We learn object permanence, we learn, intuitive physics. Baby orangutans also learn things. Here is a baby orangutan. It's playing, is being played a magic trick. Put an object in a cup, remove the object without him seeing, and then show him the empty cup, and he's rolling on the floor laughing. That's a baby orangutan. They are almost as smart as we are. If in my lifetime we could build machines that were, just a little bit, as smart as orangutans, that would be complete success. In fact, I think if they were as intelligent as a house cat, I think it would be complete success. So if you show the picture on the top left to a baby, I stole this from Emmanuel Dupoux, who is a cognitive scientist in Paris. And if you show the 6-month baby or 4-month baby, the scenario on the left here, you push a little cart off of a support and it floats in the air. Of course, there's a trick. Baby said, sure, that's the way the world works, no problem. After 6 or 8 months, they figured out what gravity is, and they look at this, like the baby on the bottom left. They're completely surprised by this, because they figured that can't possibly happen. Every object is not supported, should fall. So in fact, Emmanuel built this chart of at what age babies learn sort of different concepts, like object permanence, the fact that there are animate and inanimate objects, that's about 2 months, 3 months, stability and support, about 5 months, gravity, inertia, conservation of momentum, that's about 8 months, things like that. So, the object rigidity, things like that. So basic, concepts about how the world works are learned in the first few months of life, mostly by observation with very little interaction with the world. And we don't know how to do this with machines, but that's what we should do. So that led me to this, there is those 3 modes of learning that people use in the context of machine learning. One is called reinforcement learning. So reinforcement learning is when you get the machine to do something, you don't tell it what the correct answer is, you just tell it you did good, you did bad, right? You give it one scalar reward or, feedback once in a while. And it could be at the end of a long sequence of actions, which makes the whole thing very difficult. There's supervised learning, where you tell the machine what the correct answer is. We already talked about this. And then this kind of other modes of learning, which generally we can call unsupervised learning, but really that doesn't really tell what we do, but maybe predictive learning, where the machine learns to predict every variable it doesn't currently observe from the ones it does observe. And in that last form, there's a huge amount of feedback that the machine gets, right? If I try to predict what the world looks like when I move my head, and I do move my head, the amount of feedback I get is all the pixels in the world. It's not just one scalar value once in a while. It's all the pixels in the world. So it's a huge amount of information that the machine gets. And that's, according to various people like Jeff Hinton, this is the only way we can train very, very powerful learning machines to learn anything about the world is if we give them a huge amount of feedback every time we train them. So that led me to this slightly obnoxious slide that I show every time now because it's become a meme in the machine learning community, where if intelligence is a cake, the bulk of the cake, the genoise, if you want, is unsupervised or predictive learning, and then in terms of the amount of feedback you give to the machine. The icing on the cake is supervised learning, and the cherry on the cake is reinforcement learning, because you're only giving a very small amount of feedback, classical reinforcement learning. And that's why classical reinforcement learning doesn't apply to the real world. It works really well for things like Go and chess and things like this, but for the real world, if you want to learn to drive a car, and you have to drive the car off a cliff 50,000 times before the machine learns not to drive the car off the cliff, we seem to be able to do much better than this. Why? Because we have a model of the world that allows us to predict what's going to happen if we run off a cliff. So we don't actually run off the cliff. We don't need to do this to predict what's going to happen. Our model of the world is good enough to prevent us from doing this. So what reinforcement learning systems need to have is a model of the world. They need to learn a model of the world. And that's called model-based RL. But model-based learning in general is not just limited to reinforcement learning. It applies to all kinds of things. So reinforcement learning works well for games, because games, the world is very simple. You can simulate it very quickly. You can crash your car 50,000 times, doesn't matter. And so it works really well. For Go, of course, it's amazing how well it works. It works for games like Doom. It's starting to work for games like StarCraft, although it's still very preliminary. But this whole idea that you should have predictive models is very classical in optimal control. There's a few people here working in optimal control. And the way you do an optimal control system is you have a model of the thing you're trying to control that predicts the next state of the system from the current state and the action you're taking, or the command. And then you optimize the trajectory this way. Those techniques exist since the 60s. So why can't we do this with learning machines, basically having our learning machines learn the model of the world? And so clearly the next revolution in AI will be unsupervised. And the concept for this slide comes from Alyosha Efros from Berkeley. So, we'll need AI systems that have, you know, an AI system tries to optimize some objective, it does perception, it acts on the world, etc. But inside the agent, you need some sort of world simulator, some way for the machine to predict what's going to happen next. And I'm just going to quickly show you one example of this. Let's see, don't be scared by the fact that I'm skipping over a bunch of stuff. And first point towards a problem. And the problem is that the world is not entirely predictable. So if your world consists of two variables, y1 and y2, your entire world is, consists of 2 pixels, and the only dependency between those 2 pixels, the data points you observe, obey this law. So if I give you the value of y1, you can, to some extent, predict the value of y2. But if I give you the value of y2, there's probably 2 values, or maybe not at all, for y1 that are possible. And a priori, you're not going to know if you observe y1 or y2. You're going to have to predict the other one from whatever the one you predict. What is the best way to represent the dependency between y1 and y2? Possibly through a contrast function. So this is the idea of an implicit function. You don't have a function that computes y2 from y1 and another one computes y1 from y2. You have a function that takes y1 and y2 and tells you whether those 2 values are compatible or not. So call this a contrast function, an energy function, a negative log likelihood, whatever you want to call it. But it's something that will take low values on the data points and take higher values outside the data points. And the animation here describes perhaps what the learning process for such a function would be, right? So it's a function with 2 inputs, y1 and y2, and it produces a single output, which is whether y1 and y2 have compatible values. So it's easy enough to train a model to take low energy values for points you show it, but it's hard to actually push up the value for points you don't observe. And a while ago, I made a list of 7 different methods to do this, which I'm not going to go through, be reassured. I'm only mentioned one, which is actually not on this slide, called adversarial training. And that's because I think it's one of the most exciting developments in machine learning over the last 10 years, adversarial training. It allows us to learn predictive models under uncertainty. So here is a situation, for example. We have a predictor. The predictor looks at the past. So it looks at a segment of video, for example. It's trying to predict what's going to happen next, right? So that would be a good way for a machine to learn intuitive physics, for example. So let's say I put a pen, I hold a pen on the table, and I tell you I'm going to lift my finger. You can predict that the pen is going to fall, but you can't really predict in which direction if I do it right. So the way we're going to build this system is that the predictor is going to make a prediction, and to make his prediction, he's going to have access to a source of random vectors, called z here in this case. And so he combines x and z, runs this through some neural net, and makes a prediction for what the world is going to look like half a second in the future. And we can train the system because we can just let time pass, observe the result, and then train the machine to produce this. Problem, of course, is that if the machine predicts that the pen falls to the back and to the left, and what actually occurs is the pen falls to the back and the right, the machine was not technically wrong. It was quantitatively wrong, but it produces the wrong picture. But it kind of predicted the right thing. So how do we tell it, okay, you did it wrong, but really I'm not going to punish you for it? So what you'd like is, among the set of all possible futures represented by this red ribbon here in the space of predictions, you'd like to tell the system, if you made a prediction that is on the red ribbon of plausible futures, I'm not going to punish you. Even if your prediction is different from the thing that actually occurred, it's only if you make a prediction outside of this red ribbon that I'm going to punish you. Okay, I'm going to make you pay in the objective function. Now the thing is, you don't know what this red ribbon looks like. So the idea of adversarial training is you train a second neural net to learn the location of this red ribbon, and it's very much like this contrast function I was telling you about earlier. And the predictor is actually used to produce hypothesis samples that the other one is going to tell whether they're real or not. So that's the idea of adversarial training. This contrast function, the neural net that predicts this contrast function is called discriminator. And we have a generator that makes predictions. So initially, the generator makes bad prediction, and we train the discriminator to produce a high output, high energy output. And then we show the discriminator what actually occurred in the world, and then we train it to produce a low output, okay? So the discriminator basically learns the contrast function between things that actually occur and things that, for now, don't occur because they're predicted by the generator, which initially doesn't do a good job. Simultaneously, the generator gets the gradient from the discriminator, and so it knows how to change its prediction so that the discriminator will think it's real. Okay, so as we train the discriminator learns this contrast function, and as we train the generator trains to produce those green dots closer to the real dots and learns to do good predictions. That's the basic idea of adversarial training. You train two networks. So it breaks all the things we do in machine learning because instead of now minimizing an objective function, we try to find a Nash equilibrium between two functions, one that is used to train the generator and the other one used to train the discriminator. And, you know, that turns out to be a lot more complicated than minimizing functions. So people are working a lot on trying to make this process stable, essentially. But when you manage to make it works amazingly well. Those are non-existing bedrooms that were produced by a generator that doesn't actually look at anything other than random vectors and is trained to produce images of bedrooms. So those are randomly sampled images of bedrooms. This is work from a few years ago. Sumit Chintala is at Facebook. The other guys are at Google, I believe. There's a huge amount of progress there. I'm only showing you kind of early work on this, and this is trained on ImageNet, so you can't actually recognize the objects. These are trained on dogs. You can't, you know, these kind of funny dogs. More recent work on adversarial training by various groups across the world have produced images that are kind of amazing, high-resolution megapixel images of faces that are incredibly realistic, trained on celebrities, so you get a non-existing celebrity that kind of looks nice. This is work at NVIDIA, I believe. There's a lot of really, really cool work there in this area. But we are interested in using this for modeling the world. So if you use E² to train a convolutional net, let's say, to predict the next frames in a video, you get blurry prediction because the system cannot really predict what what is going to happen in the world. And so it produces the average of all the possible things it thinks might happen, and that's a blurry image. So that's the E² or traditional criteria produce the kind of results you see at the top right here. But if you use a bit of adversarial training, you get much sharper predictions, which may or may not be right, but they look reasonable. So those little animations, there are 6 frames. The first 4 frames are observed, and the last 2 frames are predicted, indicated by the red contour. And the predictions look okay. These are video segments shot in various New York apartments, and as the camera rotates, the system has to invent what the apartment looks like. And so it figures out what the bookcase is supposed to look like as the camera turns. The couch is supposed to continue. That there are picture frames on the wall, things like that. More interesting, if you work on self-driving cars, you'd like to be able to predict what the other cars next to you are going to do before they do it, so that it will allow you to drive defensively. So these are examples. Again, a few frames are observed, and then you predict 3 frames in your future that are spaced from, I think, a 1/6 of a second apart. So you predict half a second. And the system predicts that, if pedestrians start crossing the street, they're going to keep crossing the street. If a car starts turning left, it's going to keep turning left. The scenery is going to keep moving. So slightly more interesting with a model that I'm not going to explain. Here's a little video. So this is a little game. The paper is going to be on archive in a couple of days. This is a little game where you pilot a spaceship, and you're supposed to go to one of those colored space stations. And there is, a planet with gravity, and you don't have enough thrust to actually, go against the gravity. So sometimes you crash, but you have to figure out, the system has to figure out the trajectory. And what it does is that it builds a model of the dynamics by just learning, observing what happens, with sort of various random actions. And then it uses this model to do planning. So it's, very similar to what people do in system identification and optimal control, except here everything is learned with a neural net, essentially, a recurrent neural net. And this works much better than sort of classical reinforcement learning methods that require on the order of 4 million interactions with the environment to get anywhere and don't actually work very well, whereas this system, with 800,000 actually works okay. Okay, I'm going to stop here, and thank you for your attention, and take your questions.
Thank you, Yann. Since we have you here, I was wondering if you could comment on max pooling operation and the work of George Hinton in terms of capsule networks, and see if you could comment on when it's good to use max pooling versus capsule networks and going back and forth, basically.
Right, so there is this new recent paper by Jeff Hinton and a couple of his students on something called capsule networks. And you could think of it as a new type of convolutional net where the pooling is replaced by another operation that is kind of more explicit and tries to essentially directly manipulate the geometric parameters of parts of objects into objects. So normally in a classical convolutional net, you do max pooling. So you take the response of the filters over an area, you compute the max. And you could think of this as kind of a switch that chooses one of the activations. There are other types of pooling that people have used, but capsule is a particularly sophisticated kind. So far it's been demonstrated that this works really well on things like MNIST when you have a lot of, where you kind of need a lot of invariance to recognize handwritten digits. It's not been really demonstrated on large data sets like ImageNet, or at least it's not been demonstrated as being particularly useful. I don't think the experiments have been done yet. It's a little difficult. So it's a little up in the air whether this will really change the way we do things, or whether this is sort of an interesting idea that needs more maturing. Jeff has had ideas of this type for about 30 years almost. Rich Zemel, who was a student with him back in the late 80s, actually worked on a model called Traffic that had kind of a similar idea of explicitly manipulating coordinates of parts of objects. I think they applied this to like constellations or something, recognizing constellations of stars. And so, you know, it's taken him quite a long time to figure out how to sort of reduce this to practice to something that actually works on MNIST. He had an earlier paper 4 years ago on, you know, some version that wasn't nearly as good. So I think, you know, it's going to take a while before we figure this one out.
Okay, I don't think we have time for any more questions, but Yann is going to spend the entire day with us. And so, Chief, if you'd like to say a few words.
Yeah. Okay, well, thanks, Yann, for that enlightening talk and what is arguably one of the most exciting areas of research today in artificial intelligence and its applications. Also, as a colleague in electrical and computer engineering, so you're affiliated with our department, and on behalf of the Tannen School of Engineering. I just have a couple of other words to say. One is I would really like to thank Anna Koromanska and Raquel Thompson, who's here somewhere in the back. They put an immense amount of effort to put this series together, and so I'd like to thank you, Anna, in particular, and Raquel. Yeah. And for those students, or as to make a very bad joke, I would say whose supervised learning we are in charge of. We are, you know, I hope you take the right takeaway that this combination of mathematical insight, data, computing power, and good coding skills on your part can lead to immense benefits. So please keep that in mind, and of course, very hard work. So as we saw from all the presentation today. So again, thanks, Yann, and thank you very much. And we have this plaque for you.
Thank you. Thanks very much.
Yeah, nice talk. I'm the CSV clock, okay, now.